Hello, so today we're presenting the hyperbolic functions.
I'm Albert.
And Maddox.
Let's start with the quick mystery. This is a curve. Is it sine? Is it cosine? Is it a hyperbola? Or something else entirely?
Okay, so here is the overview of our hyperbolic function. So first of all, it's comparable to the ordinary trigonometric functions like sine, cosine, or tangent. But over here is sine h, cosine h, and tangent h. Also, hyperbolic functions are defined using unit hyperbola rather than unit circle, which can be seen by our graph. Yeah.
Some real-world applications for hyperbolic functions are cosh, of x, which is called a catenary curve, and it's one of the most practical hyperbolic functions, and it is used to calculate things regarding hanging cables, arches, and spider webs. As you can see on the right, there we have an image of some fences, and the hanging cables of those fences is what is calculated using catenary curves. Additionally, tan of x is used often in logistic curves. As you can see, 1 plus tan h of x over 2, all over 2, and is used for modeling population growth.
Okay, so here are the hyperbolic functions defined. So we can see that these are pretty simple, which are based on E and the sine h very clearly is a derivative of the cosh, which is the same thing in trigonometry, which sine is a derivative of cosine. Yeah.
You'll notice that there are some differences regarding negatives and positives, but they are extremely similar. These are the qualities of hyperbolic functions, and you'll see here, these might look extremely familiar to you. For example, qualities like cosine h squared and sine h squared are equal to cosine of h to the 2x, which is different than the usual sine of 2x, but is still extremely similar. Additionally, there are stuff like secant squared equals 1 minus tangent squared, which is extremely similar yet again, but different to 1 plus tangent squared equals secant squared.
Okay, so here are the derivatives of the hyperbolic function. So over here, so we can see that the sine h derivative is equal to the cosine h, and the cosine h derivative is equal to sine h. So it is very similar to the trigonometry, but slightly different, such as we can see in the trigonometry, the derivative of cosine h is negative sine h, but here is positive, yeah, which is different but still incredibly similar.
These are the Taylor series for sine and h and cosine of h, and they're basically the same as sine h and cosine h, not altered in any sort of way. So this is one exact similarity that we have found.
Okay, so here are the catenary curves. Yeah, so first of all, the y equals cosh for x or a, each a is a constant over here. And a guy called Leibniz first solved the catenary equation in 1690, and the most important was the interesting part explained by the GIF photo at the bottom, which shows the relationship between the catenary and the parabola, which catenary is a motion track of the focus of parabola rolling on a straight line.
Yes, and that's a picture of Leibniz on the side. So some geometric properties regarding catenary curves is that the ratio of the area under the curve to its length is equal to the Gratier-Klin constant, which, as mentioned before, is a. And that's independent of what interval on the catenary curve you select. And catenaries are the only curves on the plane to share this property with horizontal lines, as you might. If you think about that for a few seconds, that might make sense because lines have the same area below them as a ratio to their length, no matter how far you go, because horizontal lines are the same height always. Additionally, the geometric centroid refers to the midpoint of the perpendicular segment connecting the centroid of the curve itself and the x-axis.
Okay, so here is the last advanced application with the conductor capacitance. So first of all, so in my AP Physics C electricity class, I did learn the traditional formula, which is the capacitance C equals Q, which is the charge over the electric potential delta V. So over here, we're going to introduce our fourth new formula, which involves using the arc cosh or the inverse cosh, as well as as well as just two physical constants. Oh no, so not physical constant, but two just simple measurements, which are the distance between the two charges and radius, which is the where. So why will you see new formula with the Cosh H instead of the traditional formula? So the reason is for the traditional formula, we have to calculate both the charge Q and the electric potential delta V separately and using their own formulas and using a lot of different variables. If we expand them, which is really complicated and need a lot of work. However, in our new formula, we just need to do some simple measurements, such as measure the distance between the two charges and get the D, and measure the radius of the where and get the R. And after we get these two measurements, we can just plug them into our new formula, which is much easier. So here is our works cited page, and thank you for watching.